Welcome back to the channel. Today we'll be doing a slightly different video where we'll be covering questions from the Google Code Jam 2022 Qualification Round, which just concluded a couple of hours ago. In this video, we will be covering problems 4 and 5, which are the more challenging problems. Okay, so problem 4 is a bit of a long problem statement, but it's an interesting one, so bear with the explanation of the problem. Basically, the problem involves having n modules which are numbered from 1 to n. So in the diagrams here, the module number is actually indicated on the top left. So this is module 1, 2, 3, and 4 respectively. So basically, each module may point to one other module with a lower index, or it may point to the emptiness. So here, module 3 points to module 1, for example. Module 2 points to module 1. Module 1 points to emptiness. Okay, so modules which are not pointed at by any others are called initiators. So in this case, module 4 and 3. So what this person can do is they can trigger an initiator, and then once you trigger, right, it will trigger all the way to the emptiness. So for example, you trigger 4, right, you will trigger 4, 2, 1. But then it will also trigger all the way until it hits already triggered module. So if trigger 4, 2, 1, the next time when you trigger 3, right, it will only stop at 3 because 1 has been triggered before. So it will not trigger through 1 again. Yeah. Okay, so basically what happens is each of these module has a fun factor. So when you trigger an initiator and go all the way to where it stops, the fun you get from that step is the largest fun factor of all the modules that were triggered along the way. So in this case, for example, the first time he get fun of 60. The second one, because it only triggers 3 and stop there, the second step gives a fun of 40. So you get a total fun of 100 from this ordering of initiators. On the other hand, if you decided to trigger the 40 first, you will get the first trigger will proceed this way, and then you get a fun of 60. And then the second trigger will stop at module 2, which gives a fun of 50, and the total fun is actually 110. So by triggering in the other order, you actually get a larger total fun. So the whole point of this question is that you'll be given the n modules, right? You'll be given the configuration of which module points to which other module, and then you are given the fun factor, and then you're supposed to decide using an algorithm what is the order that is best to trigger the different initiators so that you get the maximum fun. So you're supposed to output the maximum fun that you can have by triggering the initiator in an optimal order. Let's take a look at the limits really quickly. The fun factor it can be large, so we will not iterate over the fun factor. The one that to watch out for is the number of modules is bounded by 10 to the power of 5. So probably something like ON or ON log n will work. Okay, so just to recap the very long question, basically you are given a forest of trees with predefined routes, because basically the module pointing to another module, I'm going to take it as pointing towards the parent along the way towards the root. So the root is the one that points towards the emptiness. And yeah, you can have multiple modules pointing to emptiness, so that's why it's a forest of trees. Okay, and they are supposed to accumulate fun by picking leaves in different orders. So when a leaf is picked, right, you walk all the way. Let's say you pick this one. You walk all the way to the root, or until you hit a previously visited vertex. So let's say you pick this leaf first, you go all the way to the root. But then the next time you pick this leaf, it will stop straight away because has been previously visited. So the fun you get along the path is the maximum fun, and then you're supposed to maximize your total fun. Okay, so obviously this problem can be solved by focusing on one tree at a time. So even though you have forest, let's just focus on how to solve one tree, then you just repeat for the other trees. So yeah, you have the root of the tree, and then what you're going to do is actually the way to solve this problem is dependent on the following crucial observation. So let's say you have this tree here, and there's a branching point here. So there's a yellow leaf and a green leaf, right? You should the question is to decide, okay, which order should I go so that I maximize my total fun? And the thing is that there's a certain amount of total fun along the yellow path, a certain amount of total fun along the green path, and then there's a certain amount of maximum fun along the blue path, right? If we let green first before yellow, then basically you have the green leaf, right, will take the maximum along the green and the blue paths, whereas the yellow will only take the maximum along the yellow path. Now, if you flip the order around, this time yellow will be the one that has a chance of taking the maximum of yellow path and blue path, but the green leaf will only have the chance of taking the maximum along the green path. So what this means, right, actually, is that if the maximum fun along the yellow path is less than the maximum fun along the green path, what you want to do, right, is you want to cash in the green but let yellow be the one with the chance of possibly upping its maximum fun, upgrading its maximum fun by moving along the blue path. So because the blue path will either go to helping to possibly up the yellow max fun or the green max fun. Obviously, you want to give that chance to the current max fun that is the lower one. So in this scenario, what you will do is you will actually activate yellow first, so that yellow has the chance to tap on this, and then green will stop here. So we will add green to the answer, and then yellow will continue to bubble upwards as the leaf that will tap on the blue path. And conversely, if the maximum fun along the green is the smaller one, we want to give green the chance to possibly upgrade its max fun by tapping on the blue path. Whereas yellow, we will just add to the answer. So green activates first, then yellow will be stuck to whatever its max fun is. Okay, so this is the crucial observation and actually basically tells you how to solve the problem already. What we'll do is we'll bubble upwards the answers using a standard DFS approach. So basically what you do is using some DFS approach, right, you can bubble values upwards from the leaves towards the root. And what are these values that we store? So basically we initialize all the leaves, right, to have the DP value of the leaf, right, being the fun value. So FV refers to the fun value of vertex V. DP is the value that we are interested in to bubble upwards. So, well, if the node, right, is basically along the path, then you just bubble upwards the maximum fun so far along the path by taking the max of its own fun value and the DP of the child immediately below it. So far the DP stores the maximum fun along the path that is being traveled by that leaf chosen. Okay, now the crucial part comes at the junction. So let's say you have multiple children. What do you do? So there's a DP value here, here, and here, right? This DP value, for example, it stores the current maximum fun of the path, right, of the leaf that is being currently bubbled all the way here. So it's the most noob leaf because we want to give the noobest leaf the chance of tapping on the higher paths, but it is the maximum of the max fun of the path taken by the noobest leaf noobest leaf. So what you do is you have the DP values here. You find out which child actually has the minimum DP number. So that will tell you which leaf is actually the noobest leaf. Now, the other children, right? We will kill it off because we are only going to continue to bubble the noobest leaf up. The others are reach the end of their game, right? Because once we do the noobest leaf first, the rest of the children will be stuck here. That's the end. So we'll add DP of the other children to the answer. That's the fun that they will contribute. And then we'll bubble the noobest leaf up as the choice that will tap on this vertex and beyond. So to do that, the DP value of this will be updated to the maximum of its fun value and the DP of the noobest of the child, which corresponds to having the noobest leaf bubbling upwards. Yeah, so this is the DP update. And then, of course, you continue to iterate this by using a DFS approach. The children will have been computed by the time we reach the parent. So we can use keep bubbling upwards until we reach the root. And then don't forget, DP root currently stores the fun value that you will get by activating the super nubus leaf first. So don't forget to add it at the end to your answer as well. Okay, so that is all for problem 4. With this algorithm, it will be a ON solution because you are basically traversing along the edge once to bubble up all the values. Okay, so that's all for problem 4. Let's take a look at problem 5. Okay, so problem 5 is actually a very unconventional problem, and as of the time of recording this video, there are less than 100 people who have solved it so far, even though like almost half a day have passed. So it's actually unconventional. Let's take a look at problem first, then I'll make further comments. So basically, you are investigating a cave, which is basically a simple undirected graph on n vertices with no isolated vertices, so something like this. So you're not given actually how the graph looks like. You're only told firstly the number of vertices, which is according to the limits of the problem, it is less than or equal to 10 to the 5. Okay, then at the start you are given a vertex number that you are currently standing at, and then the number of incident edges to that vertex. Now you are allowed to explore the cave by making up to 8,000 moves. So each move, right, is either teleport or walk. So by teleport, you can choose a vertex number of your choice, and then you'll be teleported to that vertex number. If you choose to walk, you will be moved uniformly at random to a neighbor of the current vertex. So if you're at 1, right, you don't get to choose 2, 3, or 5. Instead, you'll be randomly moved to 2, 3, or 5 with 1/3 chance each. So after each move, you are told the vertex number you are at and the number of incident edges to that vertex. The goal of the question actually is to estimate the number of edges in the graph. Of course, there's no way you can get it like 100% correct. So you're actually allowed a very large error margin. Actually, it's a 33.3333% error margin. And you are required to succeed at least 90% of the test cases. So the error margin is actually super big, but you might think it's super big, but actually not really. So for this type of problems, I would say there's really no pure scientific, like definitely correct way of doing it. Somehow it's a visible verdict problem. So it's quite similar to last year's qualification problem 5, where basically you need to implement enough heuristics so that you are fairly certain that you are close to a good enough estimate. And then you try out submitting a solution and see whether it is accepted or not. Yeah, so the whole point is heuristics is based on like intuition. There's no 100% way of saying this is definitely the best method or so on. So let's see how what is one reasonable way to come up with a good way to estimate. Now, obviously, the first thing you might realize is if the number of vertices is at most 8,001, right, then you might as well use your 8,000 teleport moves and then visit all the vertices so that you will be able to find out all the degrees. And then basically the number of edges is their sum of degree over 2. Okay, so that is quite straightforward, but that gives you an idea. If it's more than 8,001, maybe we can just use teleport to visit 8,000 randomly chosen vertices and then use that as a sample to estimate the average degree of all the vertices and then similarly compute this. Well, this kind of works except not really, because I mean if your graph is constructed randomly enough, this have maybe a good chance of working, but your graph can be some super evil graph. For example, it might be a star, right? And okay, here I only show 5 leaves for simplicity, but imagine you have 10 to the 5 vertices. A star will have 99999 of these leaves, right? And if you are to teleport to 8,000 randomly chosen vertices, right, chances are you will hit like 8,000 leaves and you will not hit the center. Then your sample will estimate that the average degree is 1. So your estimated number of edges is actually n over 2 because estimate average degree 1, so times n vertices, but divide by 2, so yeah, n over 2. But the actual number of vertices, the actual number of edges is actually n. So you're like 50% off. So that's not good. What the problem is, your sampling will hit all the leaves with very high probability and not miss the center. So one way to possibly fix this is, well, instead of just teleporting, maybe you teleport to an unexplored vertex, and then you make one walking move, so that in the case of a star, right, chances are you hit a leaf, but then when you do the walking, you hit the center lah. So, and of course, I mean, it's not the case that only a star will mess up the sampling idea. You could have like 3 stars connected together in some funny way, or like three spots in the graph that looks like star-like. So the whole idea is there could be some centers with very high density and then very high degree, but your sampling will miss them. So you want to find a way to actually catch these outliers, and walking one step will at least have some chance of like walking towards the basically the high degree centers. So I'm going to repeat 4,000 times this teleport plus walk approach, where each cycle basically gives me a sample for 2 vertices. Obviously, I'm not going to if I teleport, I mean I'm going to choose an unexplored vertex just to like maximize my chances of seeing something new. But then after you walk, you might hit back a vertex that you explored before. So I'm going to just use a dictionary to store the degrees to make sure I don't repeat vertices that I've seen before. Okay, and in case you're wondering how to randomly choose vertices in an efficient way, I mean, you just need something pseudo-random. You don't need to be like completely like scientific about this. So what you can do is you can pick a prime number like in the 4,000s and a prime number in the 3,000s or something. Then you basically start from the prime number and keep adding the other prime number to generate a sequence of numbers that will not repeat itself, modulo n, and then like use that sort of like a pseudo-random kind of chain of numbers to teleport to lah. So anyway, okay, so now we seem to have solved the problem of missing high degree vertices, except we compensated for that too much. Actually, if you think about the example of the star again, we have like maybe like 3,999 samples of 1, and then like 1 sample of like 99,999 degree, right? So that if we take a simple average of the sample, that outlier of like 99,999 degree, right, will pull up the average so much that it will again skew the data in the other direction, right? Because actually the average degree should be like there's 99,999 leaves and 1 center, but because your sample is only 8,000, right? Up to 8,000 after you remove the repeats, you have not enough leaves to pull down the average. So now your estimated average degree is too high. So the crux of this problem is that you want to capture the outliers, but then now your outliers are skewing the average in the other direction. But there's a simple way to fix this. Basically, you sort the data that you have in decreasing order of degree, and then you basically add the first like 200 as you like maybe segregate the first 200 and call that your outliers. 200 may seem like a lot, but you actually have like at least 4,000 sample points, so 200 is like 5%. So you just like say the first 200 is outliers. You add directly those degrees up towards the total degree, but then you estimate the remaining n minus 200 vertices, right, by taking the average of the remaining data that are not called outliers. and then you just take the average multiply by n minus 200, and then you add that to the total degree, then take total degree over 2. And yeah, so actually this x part, the numerical value of x is also heuristically determined. I just chose 200 and it works on the first try. So I think something like 100 or 50 might also work. That's all for this video. Next week is actually Google Code Jam 1A. So stay tuned and see you soon.